Hello. We are going to talk about circuit analysis. This is going to cover a wide range of stuff, and we're going to go pretty fast through it. So make sure that you are pausing if you get if you need a second to catch up. Make sure that you understand, where we're coming from before you get to where we're going. So don't go on in the video until you're sure you've understood what's already happened in the video. Hopefully you will understand that well enough to go forward. Otherwise, you're going to get stuck in a recursive loop pretty fast, and don't worry about what recursive means. Anyway, this is a circuit. You can tell it's a circuit because it is a closed loop of stuff. And so now let's talk about what the stuff that what stuff is in here. Oof, English. We have a few pieces that are useful. We have a battery. A battery is a source of voltage. Voltage, a new word for us, but basically it's a measure of energy, specifically electric potential energy. So what this is doing, the battery is supplying electric potential energy for the charge that moves around in this circuit. Now this charge that's moving around in this circuit is moving through these wires connecting the elements in our circuit. Elements in the circuit just being any pieces that we're putting in this thing. When we talk about an ideal wire, that's usually what we're going on. It's something that we can have as much or as little of, and all it does is connect things. It doesn't impact the circuit in any other way. So I could draw the circuit as I've done right now, or I could draw it like this, and it is the same, functionally speaking, but it's a little neater if we just kind of stick with the straight lines. And this last thing down here is a resistor. And a resistor, shockingly enough, resists. So the strength of a resistor is a measure of how difficult it is to move charge through the circuit. Whew. The circuit. Writing takes time. All right. So we said we're moving charge through it. And if we're connecting these things with wire, if we think most wires that we know of are metallic, copper wires, for example, are a really common example, which means that they are, hopefully you just said the word conductor to yourself. If not, rewind the video and in that nice, dramatic pause, say conductor. It'll make you feel good. All right. So we know that there is charge that's freely able to move inside of this circuit. And what we're going to do is that charge that's moving, we're going to call a current. And so current is the rate at which charge moves. Through a circuit, but that's through a circuit is getting tedious to write, so we're moving on. So the big things that we want to worry about, though: voltage, resistance, and current. Conveniently in a different order than I just said. So current is the rate at which charge moves. Just going to literally rewrite what we just said. And we're going to measure it in amperes, which we abbreviate as an A. 1 ampere is 1 coulomb per second. So if you have a 1 amp current, 1 coulomb of charge goes by every second. Voltage and electric potential energy are not exactly the same thing, but you can think of it as a measure of the electric potential energy in the circuit. Strictly, it's the electric potential energy per charge, but we're not going to worry about that. Ooh, writing. The unit of voltage is, shockingly enough, the volt. All of those puns were intended. And 1 volt is 1 joule per coulomb. Let's try to be consistent with how I did this. So it's saying the battery says, I'm going to set up a voltage. And so that means that, if I have a 1 volt battery, it gives 1 joule of energy to 1 coulomb of charge. All right? It's like it's saying like how big your hill is. If I have a hill that's 10 meters tall, it gives 100 joules of energy to 1 kilogram. Because if I were to go mgh, I would see that 1 kilogram would get g times h joules of energy. 10 times 10, 100 joules of energy. And so resistance, we said, is a measure of how difficult it is to move charge through a circuit. I'm just going to say move charge. And so resistance is measured in ohms. And an ohm uses the Greek character omega. An ohm is an ohm. It doesn't really have it's not a derived unit in the same sense that the volt and the amp are. I should point out this is often just called amp. So amps. Which is not the same as an amp, like an amplifier, which does something totally different but also depends on amperage. English is hard. All right, so you might be wondering, we've got these ideas, how do we relate them? So one of the things that we're going to go over in class, we're going to play with this little idea, is the idea of Ohm's law. So Ohm's law, same ohm that we named resistance for, tells us about the relationship between voltage, current, and resistance. It basically says that for a given voltage, so if I hook a battery up to a circuit, and I hook up a resistor to that battery, I will drive a specific current. For example, let's go back up to here. We got this nice circuit. If this is a 5-volt battery, remember batteries are a source of voltage, so I'm measuring this in there. And so that's VBAT. And this resistor is, let's say, a 10 ohm resistor. Then Ohm's law tells me that delta V for a resistive element like this resistor equals IR. Well, the change in voltage for this battery, or for this resistor, is just the battery's voltage. If I go around this loop, I see that all this voltage I'm getting from the battery, the only thing that goes into is this resistor. Because again, my wire is ideal. And now we can say more precisely what that means to have ideal wire is that it has no resistance. So, if delta V equals IR, then the current in my resistor equals delta V over R. And if that's true, we said delta V was 5 volts. We said R was 10 ohms. So I is 1/2 of an amp. As before, when we're dealing with SI units, if we put everything in the base SI units, we get base SI units out. It's nice like that. So take a second, make sure you're okay with this so far. This idea of voltage, current, and resistance. Voltage, kind of a measure of energy in the circuit. Resistance, a measure kind of friction of how much energy it takes to move through a circuit, or how hard it is to move through a circuit. And current, a measure of how fast the current is moving, of how fast the charge is moving through the circuit. Just because you have a high current doesn't mean you're delivering a lot of energy. So do be careful. The current is not what's carrying the energy, it's the rate at which the energy is being carried. Right? Imagine that you're, filling up pails of water at the battery. The current is how fast you can walk with the pail of water. It's not how much water you're carrying. The water in this case is your electric potential energy. That depends on the voltage of the battery. Now, you might wonder, well, Ohm's law is good, but it seems like it only works for one resistor. What if you had 2 resistors, say, in one of these configurations, which we're going to call series and parallel? So these 2 resistors, R1 and R2, are in series. I guess I actually should have named these in the other direction. Because, and by the way, positive terminal, negative terminal of the battery by convention. Positive has the longer end, negative has the shorter end. If you look at a battery, you'll see that it has a positive and a negative end. Usually, for a physical battery, the positive end is the bit that has the little nib on it. Looks something like that. But we're all into idealized representations, so 2 parallel lines. Anyway, resistors. We say R1 and R2 are in series because if I go around this loop, if I go through R1, I must go through R2 to close my loop, to complete my circuit. Now over here, I'm going to have R3 and R4. Actually, I'm just going to call them R1 and R2 again. It's just different circuits. Now these, I'm going to say, are in parallel. And they're in parallel because if I go through R1, I can complete a circuit without going through R2. Similarly, if I go through R2, I can complete a circuit without going through R1. So if they're in series, I can think of this as a giant AND. I go through R1 and R2. If I have them in parallel, I can think of this as a giant OR. I go through R1 or R2. We might see circuits where you have something even more complicated than this. Maybe some things are in series and in parallel. And you need to figure out, are things definitely in series? If I go through one, I have to go through the other, or are they in parallel? And the most common example of this is something like this. R1, R2, and R3. A battery, I guess, to make it nice and complete. And so you might be wondering, is R1 in series with R2? Is R2 in parallel with R3? Is R3 in parallel with R1? Is R1 in series with itself? Well, it's not in series with itself. That doesn't happen. Take a second and figure out for yourself, and let me know if you're having trouble with it, what you can say. Is which resistors here are in series with each other and which are in parallel with each other. Anyway, once we have this, we have rules to combine them and bring them back into just one resistor to find what we call the equivalent resistance. And that's these two expressions down here. Having trouble with my Zoom. So this REQ, EQ here is standing for equivalent, is the equivalent resistance of R1 and R2. If they're in series, I take R1 and R2 and I add them. And that will produce a new resistor that has the equivalent resistor of the equivalent resistance of the ones that I replaced. So I can take out those two in series and put in instead a new resistor, different resistance, but behaves the same way in the circuit. The circuit can't tell. So the battery will supply the same current to that new resistor. It acts the same way. Similarly, if they're in parallel, I get this slightly more complicated expression where 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2. So let's come back to these and finish out these examples. Let's say that this is a 4 ohm, no, let's do something that's probably not on the homework. Let's say this is a 20 ohm resistor and a 5 ohm resistor. Then, if I follow this, what this is telling me is that the equivalent resistance should be 20 ohms plus 5 ohms, which would be 25 ohms. And so if I were to go through, I would discover that these two circuits where this is a 5 ohm and this is a 20 ohm behave the same way. And this is something we can test in class. Similarly, if I were to come over here and again see a 20 ohm and a 5 ohm resistor, I would come down to this expression and say that 1 over our equivalent equals 1 over 20 plus 1 over 5, which, because I am exceptionally clever and picked numbers for once that aren't going to cause me any trouble, I can get a common denominator, and I see that this is 5/20ths, which means that if 1 over our equivalent is 5/20ths, our equivalent is 25ths, or, as we more commonly refer to that, 4, which means that this circuit with a 20 ohm resistor and a 5 ohm resistor is equivalent to this circuit. And that might be weird to you. You might be thinking, how did I add a resistor, in theory making it more difficult, but got a smaller resistance? I got a circuit where it's easier to go through it. So I want you to think about that for a bit and think very carefully. Well, if I had, for example, a 1-lane road versus a 2-lane road, is it easier for traffic to go through it? That's a similar kind of problem. By opening up the second branch in parallel, you have in fact made it easier to go through the circuit. Now, we'll talk about these things some more in class and work through some examples, but these are the basics that you need to know to get started. All comes down to these ideas of voltage, current, and resistance. All right, good luck, have fun.